Today we're going to be looking at nuclear radiation. It says nuclear decay, but I think really it should be saying nuclear radiation. We're looking at the radiation, the results from decay. So a bit of revision. An alpha particle is a helium nucleus. It has 2 protons and 2 neutrons. It is heavily ionizing because of the double positive charge. It leaves thick tracks in a bubble chamber as a result. It is absorbed very quickly and easily as a result. As it causes ionization, it loses energy and slows down and stops. It's dragging all those electrons behind it, so they cause it to stop. The alpha particle tracks are also straight. That's a reflection of how massive an alpha particle is. Alpha particles have a fixed, discrete energy level. If you know the decay that's causing the emission of the alpha particle, then you know the energy of the alpha particle. Alpha particles are deflected by a magnetic field because they have a charge and they're moving. The left-hand motor rule predicts that they will be deflected. The deflection is perpendicular to the movement of the alpha particle and to the magnetic field. They are mutually perpendicular. Beta particles. A beta particle is just a fast-moving electron. The nucleus consists of protons and neutrons. There are no electrons in the nucleus. However, a neutron can change into a proton, and in doing so, an electron is formed and it is ejected. It's ejected at high speed. So, whilst an electron is any old electron, a beta particle is an electron that's been ejected from the nucleus of an atom. Electrons have a single negative charge, so do beta particles. They are therefore deflected by a magnetic field. The deflection is in the opposite direction. They are light. They are strongly ionizing, but not as strongly ionizing as alpha particles because of the single negative charge. As they lose energy and slow down, the rate of ionization increases. Sometimes I think that's paradoxically. But the reason is initially they're traveling too fast to have much effect. Whereas as they slow down, then they can exert a force for longer and therefore push an electron out of an atom. So gradually they slow down and stop. Maybe they'll travel 20 or 30 centimeters in air. So to stop a beta particle, you need something a bit more substantial. People generally say a few millimeters of aluminium. Beta particle tracks in a bubble chamber are wispy because the ionization isn't very great. They're also crooked because the beta particles are light and get knocked around. And the most important thing about beta particles we will come on to look at later. Finally, gamma particles. Or is it gamma radiation? What's going on? Is it gamma particles or gamma radiation? We often hear of gamma being referred to as radiation, and yet you can count gamma with a Geiger-Müller tube and a counter. So they must be particles, shouldn't they be? The gamma radiation is simply a blast of electromagnetic radiation, energy. The gamma radiation has a certain frequency. Each photon of gamma radiation obeys the formula E equals hf. They're given out after alpha or beta decay has occurred in general, when the nucleus is left in a slightly unstable, high energy, excited we usually call it, state. So it then settles into a more stable state by emitting a gamma photon. The gamma photons have characteristic energies depending on the source of the decay that is causing them. Okay, well, that's enough of the introduction. We've covered some of the new ground, but let's move on. Here's a video you can watch. It's a bit of fun. It's only 3 minutes long. It'll revisit some of the stuff that I've said. And it features a rather charming man with a Scottish accent. And here we notice that it says triumphantly that with 241 americium decay, our alpha particle is emitted that has an energy of 5.638 megaelectron volts. We'll be looking at what on earth we mean by megaelectron volts, and we'll also be considering why it's possible to quote that value to 4 significant figures. And here's a formula for beta emission. And another video, 3 minutes long, I believe, with the same rather charming Scotsman. So have a look at that and see if you reckon that the little beta particle man is as ridiculous as the alpha particle Superman. Oh, and some of you will have spotted with your eagle eyes that we've got a third element in the decay products. 14,6 carbon decays to 14,7 nitrogen, plus the beta particle, plus something that's got no protons and neutrons and no protons. In fact, it's not very much at all because it doesn't seem to feature in the numbers. Well, this is an antineutrino, and it is the clue to why it says the beta maximum kinetic energy is 0.156 megaelectron volts. So it's not fixed. It's only a maximum. So moving on. Well, here's a little bit more about the story of beta decay. When beta decay occurs, you get a spectrum of possible energy levels. And for a while it was thought that somehow or other this was contravening the conservation of energy. Because if the carbon-14 has a fixed mass and therefore a fixed energy, and the nitrogen-14 has similar, then surely the beta particle should have a fixed, regular, predictable energy level, not a varying or spectrum of possible energy levels. It was surmised that the extra energy must be made up with another particle, very hard to detect, and it was eventually discovered, and it is, in this case, an antineutrino. Not a neutrino, it's an anti-electron neutrino, as it happens, and it makes up the difference, that the energy that's missing. These neutrinos are very, very hard to detect. They're incredibly weakly interacting with matter, and all the experiments designed to detect them use great vats of, I think it's heavy water, positioned down a mine somewhere. The idea of the mine is so that all the extraneous other radiation is absorbed by the thick chunk of earth. This is a seminal picture. What's happened here is that there's been a decay of some nucleus, I'm not sure what type, at the junction where the 3 arrows meet here. And the nucleus has gone down to the left in a sort of southwesterly direction, and the beta particle has gone down to the right in a southeasterly direction. So that means that unless the conservation momentum is not working in this case, there must be something that goes north. And that something is the antineutrino. Now, the antineutrino leaves no trace because it has no charge and it's too weakly interacting. But we can clearly see the nucleus moving, we can see the beta particle moving, we can see the beta particle curving because there is a magnetic field. But we can't see the antineutrino, but eventually it was discovered. Well, I've said this about gamma emission. I mean, typically gamma emission is about a megaelectron volt, and whilst beta particles may travel at close to the speed of light, gamma radiation, of course, travels at the speed of light. Gamma radiation travels an awful long way in air. It's rarely absorbed. It's rarely absorbed passing through us, which is just as well, because otherwise we would suffer. And it therefore, as it spreads out from a point source, it obeys the inverse square law. And if you do want to protect yourself from gamma radiation, you need 2 or 3 centimeters of lead, or most people say a meter of concrete, and you will absorb most gamma radiation. Gamma radiation can vary in energy levels. The cobalt 60 that we use produces 2 gamma particles of about a mega electron volt. Another material or isotope that's particularly important is technetium-99m. The M stands for a metastable state. After the initial emission, the technetium-99 remains in this excited state for quite a long time, so as it has a half-life of its own, and then it decays by gamma emission. And this makes it extremely useful in medicine because it can be injected into humans, and because there's no alpha or beta associated radiation, then it can be used to track the flow of blood, for instance, around the body using a gamma camera outside the body. So that's technetium-99m. Its half-life is it a few days, maybe 6 or 7. So you have to keep making it afresh, but that's easily done too. So technetium-99m is very popular with doctors. Now, come on, baby. Okay, here is the chart of the nuclides, as it says. The chart of the nuclides. Dum, 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 dum. And it's worth noting that on the x-axis, we've got neutrons, and on the y-axis, we've got protons. Did you notice how cleverly I corrected my initial error there? On the y-axis, we've got protons. On the x-axis, we've got neutrons. So you can find any nuclide on this chart, and each nuclide is represented by a box. Now, what I wanted to emphasize here is that the chart goes from bottom left to top right in pretty much a straight line. It bends slightly to the right, I would suggest, if you squint along it, so that as the nuclei get bigger and bigger, you need more neutrons to hold them together. So initially, we've got approximately equal numbers of protons and neutrons, but as the nuclei get bigger, if you think of something like uranium-235, 235 total nucleons, only 92 protons, so well less than half. And yet down here at the bottom, we start off with something like helium, and it's got 2 protons and 2 neutrons. So what else have we got? We've got carbon-12, that's 6 protons and 6 neutrons. And then we've got oxygen-16, which is 8 protons and 8 neutrons. So initially, that works extremely well. It's a very stable arrangement. But eventually, as you get bigger and bigger nuclei, the force of repulsion between the protons becomes greater and greater. So to overcome that, you need more and more neutrons. And the neutrons, and indeed the protons, when they're very close together, subjected to they feel the strong nuclear force, which overcomes the force of repulsion. This image shows the boxes more clearly. You still can't read the data. Each box has got lots of data on the radiation emitted. It's chopped up, so I wanted to show you the previous picture so you know that this is a continuous chart. It's not 3 chunks. It goes from bottom left to top right, but we've still got the same idea. On the y-axis, I've got it right this time, we've got protons, and on the x-axis, we've got neutrons. Looking at the color code, the black squares are stable. So you might say, well, how do we know about all these pink and blue ones? Well, for a long time, physicists were engaged in just filling in the blanks and just trying to find out about all the possible squares. And there was also the competition to see who could make the heaviest nucleus possible. This is a competition between the Americans and the Russians. So up at the top there, you find nuclides called what should we have? Californium and berkelium, and also lawrencium. I'm surprised there wasn't a starlinium or a leninium. But anyway, only the black ones are actually stable. Now the pink are beta emission, and because the pink is beta emission, then when a beta emission occurs, then it goes just one box in a northwesterly direction, because you gain one in the proton direction and you lose one in the neutron direction. The blue or turquoise squares are what's known as beta plus emission. And beta plus is a positron. So a box, get out. This time they'll go from a box to one diagonally in a southeasterly direction. So a positron is an antimatter particle for an electron. And so that's why it goes the other way. It has a single positive charge, but in all other respects, it is the same as an electron. A beta minus particle, it's an antimatter particle. Yellow squares are alpha emitters, and so what will happen there is that they'll lose 2 protons and lose 2 neutrons. So shifting downwards, 2 down, 2 to the left, and the yellow squares are for the big nuclei. And there are 1 or 2 exceptions to that, but generally. And I know you want to ask what the green squares are, but to be quite honest, I don't know. We'll have to look that up. Now, finally, I want to talk about the secret, the underlying reasons as to why some of these nuclei are stable and others of them are unstable. This is the binding energy curve. And if we remember Einstein's famous equation, E equals mc squared, then we can find out what the energy level is of an isotope by measuring quite simply measuring its mass. And we find that when particles fall together, so to speak, into a nucleus, they lose mass. So, for instance, if you take 2 protons and 2 neutrons and you work out their total mass, it's more than the mass of a helium nucleus. It's not hugely more, but it is measurably more. And the binding energy could also be expressed as the mass defect. It's the difference between the mass of the 2 protons and the 2 neutrons and the mass of the helium nucleus. It's the mass that seems to have disappeared, and that's because those 4 particles have fallen to a lower energy state. And here we look, here is helium-4. It's particularly stable. Above it you can see carbon-12, oxygen-16. These isotopes are very stable, unusually stable. Now, it is the case that this graph is not a smooth curve because they are discrete points, but we can still imagine a kind of curve that goes up steeply on the left, reaches a peak, and then slopes down to the right. So this explains why nuclear fusion is when individual particles fuse together to form typically helium or carbon-12 or oxygen-16, And that is fusion, which leads to the release of energy. But coming the other way, we've got nuclear fission. Fission is where a very big nucleus splits into smaller ones. But we can see the smaller ones are more stable. They have higher binding energy per nucleon. And therefore, the particles involved in those large nuclei have fallen to a lower energy state and released that energy. So typically, we're getting, well, for helium, there are 7 mega electron volts per nucleon. So let's have a look and see how it is that the helium formation of the helium nucleus can cause the release of so much energy. I think I've got a couple more pictures to show you. So we'll just pause here. You can pause the video to have a look at some of the data that's on here. We noticed that the iron group are the most tightly bound group of isotopes. And here the line's just been sort of inked in. It's the overall rough shape that's of interest. And this particular picture I particularly like because it's got 3 axes. It's got the binding energy vertically, but it's got proton number and neutron number. And so here you can see the steep curve coming down and then going gradually up, but you can also see the curve going from side to side. So down right at the bottom of the valley are the black squares that are stable. And you can tell even the dog thinks this is interesting, barking away. Now, in this case, the binding energy is shown as negative because the mass has actually gone down. And we quite often think of when particles fall together, they go to a lower energy state. So if we have 0 as being when their particles are infinitely far apart, then binding energy is negative. But it doesn't particularly matter. It's either way around, as long as you understand what it means. Pause the video and have a look at what it's got to say on this chart. There's plenty of information on it. Well, here are some numbers for fission. The mass is in U, also known as atomic mass units. It's just related to 1.66 times 10 to the minus 27 kilograms, which is roughly the mass of a proton or neutron. And if we consider the uranium that we start off with, going to technetium, is it zirconium? Actually, that's not technetium. What is it? I can't remember what that's called. Technetium is it technetium? I can't remember. And a neutron. So we can then work out how much energy is released in this fission. So here's the calculation. Oh, spot the typo. There is a typo in this slide. I'm afraid there's no Mars bar for spotting what it is. I'll leave you to correct that. We can work out that the change in mass is 0.216 atomic mass units. There's the 1.66 times 10 to the minus 7 is the mass of 1 atomic mass unit. And then we just need a calculator to work it out. It's worth noting that 1 electron volt is 1.6 times 10 to the minus 19 joules. You might like to look up why that is. It's also worth noting that this is a lot of mega electron volts, but it's the total. So the number of mega electron volts per nucleon is less than 1. So that reflects the shallow gradient of the binding energy graph for fission. So let's now look at fusion. Well, here's a picture that shows 4 nucleons, 2 protons and 2 neutrons. Actually, they're about to become nucleons. They're just separate at the moment. And we see that separately, the mass of the 4 of them is 4.03188 atomic mass units. But together, in the nucleus of a helium atom, their mass is significantly less. So again, we can work out how much energy is released when these 4 particles form a helium nucleus. The same typo. Can't believe I'm so good I did it twice. But the same idea. Here's the change in mass. Here's the exchange rate for 1 atomic mass unit. I haven't got a calculator with me that does scientific notation at the moment, so I'll leave you to work out the question mark and to confirm that the answer is 28.3 megaelectron volts. Here we've got 4 nucleons involved, so that's about 7 megaelectron volts. 7 megaelectron volts per nucleon, as per the binding energy chart. So, we've looked at alpha, beta, gamma radiation, and we've looked at some thinking behind why fission and fusion occurs, and both of them cause the release of energy. So that's all we've got time for today. Thanks for listening.